I'm Ed Mathews. I am one of the, I think we're being called the old fellows right now. I think that is what we're branding us as. And so today I'm going to be talking about some work I've been doing on blue waters using large-eddy simulation, LES, to study aero-optic distortions. This has really been because of the generosity of the Blue Waters program for letting us continue working past our fellowship and giving us allocation and time on the supercomputer. So thanks a lot to Blue Waters for that opportunity. And I also like to acknowledge my collaborators on this, Can Wong, who's a postdoc at Notre Dame in our Aero-optics group, and my advisors, Meng Wong and Eric Jumper. So what is aero-optics? It's not really something you always hear about when you hear about turbulence and fluid dynamics. But in short, it's the distortion of an optical beam propagating through a turbulent field, and it gets distorted by density fluctuations in compressible flow. So we can relate the index of refraction of a fluid to the density of the fluid itself through the Gladstone-Dale constant, which you see here, index of refraction density, and then this is the Gladstone-Dale constant. Normally we talk about this in terms of the OPL or the OPD, which because these index of refraction fluctuations are really weak, you don't get a lot of scattering. So you can just use ray tracing to propagate through. So you can look at this in terms of how does the local distance increase or decrease as you propagate through. So you're talking about a wavefront, and it gets distorted as it goes through. And the relative distortion is what we call the OPD, which you just, after the integration, you take out the time mean. So it's also related to the local phase distortion of the wavefront. So what this does for a certain case, especially with modern low wavelength lasers, is that you have an initial beam. If it doesn't get distorted by aero-optics, when you look to the far field, it'll kind of go out, and if you have the Aries disk kind of structure of your beam, you have this a little bit of diffraction that happens to it, but you don't really lose a lot of intensity or fidelity of the signal. But if you propagate for a low wavelength beam through an aero-optic distortion, as you start going further and further out, you lose a lot of the quality of the beam and the fidelity. So if this is a signal that you're trying to send from plane to plane, or you're propagating through some kind of compressible flow that you're trying to communicate, or you have directed energy purpose, this could be a huge hindrance to the system. So the current work on blue waters is a continuation of what I did last year with the fellowship. Mainly this simulation, which is the optical turret that's used on Notre Dame's Aero-optic laboratory, which is a really unique laboratory. It's two jets that fly around by northern Indiana and Michigan, and they pretty much beam a laser between them and then look at the optical distortion. So I'm kind of running the simulations to compare and validate and look at some of the physics that maybe they can't get out of these really, really well done experiments. And then I've kind of continued this a little bit more fundamentally by looking at LES of a low compressible Mach number mixing layer to kind of investigate the connection between aero-optics fundamentals and the flow quantities themselves. So the flow solver I'm using this term, large-eddy simulation, which solves a spatially filtered version of the Navier-Stokes continuity and energy equations. And then for everything that we don't resolve with the grid, we model. So this really it helps out when you have engineering type problems or really high Reynolds number problems where the resolution that you need to attain to get the whole range of turbulence is really, really limiting. The solver itself that I'm using is an unstructured mesh compressible LES code called Charles. It's developed at Cascade Technologies, which is an offshoot of some work that was done at the Center for Turbulence Research at Stanford. And then just a little bit of information about the solver itself. It uses a kind of interesting spatial numerical scheme, so it's finite volume, and then it uses primarily central flux, but it uses also a dissipative upwind flux in areas where the grid resolution or the skewness of the grid isn't really conductive to having a stable numerics. So this is the amount of upwind, though, is really minimized and it's local it's like I said, determined by the local mesh skewness. So if you're really good with your mesh and it does take some iterations, you can really maintain a high quality simulation still. Formally, it's second order, but the nice thing about the flux reconstruction is that in uniform Cartesian meshes, it has a fourth order instead of the second order. And then for the turret simulation that I'm going to be showing, we used a wall model, which solves on an embedded grid. I'm going to talk about it in a second, a set of pretty much RANs and inner part of the boundary layer, and then provides approximate boundary conditions for the wall. We use RK3 in time. And then this subgrid model that I talked about is kind of really key to a large-eddy simulation. I'm using the Vriemann model. And then Charles is fully parallelized using solely just MPI. So this wall model method is really kind of fundamental into us studying these high Reynolds number flows. Because if anybody was in Dr. Leorf's talk yesterday, you kind of know a little bit about how hard it is to resolve near wall in turbulent simulations. So to kind of alleviate that, this is an approximation for having that really high resolution in the wall. So instead of really overloading to resolve those near wall scales, we embed a separate mesh in the LES mesh. We interpolate at every time step to this wall model mesh, solve an ODE, and then for the velocity and the temperature distributions, get a shear stress out of that, and then use it as approximate boundary conditions at the wall. So the whole goal of this is that where you have LES and you have engineering systems and you want to do it at the real Reynolds number that is really restrictive, you can now do it where before it would be insanely expensive. So talking about this hemisphere on cylinder turret simulation, I've kind of breezed through all the boundary conditions and setup. But this turret it's half of a sphere sitting on top of a cylindrical base, and that's mounted to a wall. The incoming flow is Mach 0.4, so it's not, you don't have shocking yet, but it's fully compressible. And the Reynolds number that you can see here is really large, is at 2.3 million based on the turret diameter. So here I have for two different meshes, which is the Coarse mesh is something I've done this year. And then the fine mesh, which is the Coarse mesh is 2/5 of the fine mesh size. So what are we interested in here? Of course, knowing stuff about the fluid dynamics from the simulation and the aerodynamic quantities is important. But this is an aero-optics problem. We want to know, how does the optical distortion change with where we're looking? How can we connect that to the fluid dynamics? And then ultimately, can you use this information from the flow field to provide some kind of correction to the optical wavefront so you get a clean propagation through this fluid dynamics field? So over the past year, we've doubled the runtime of the finest simulation to get better convergence of statistics. And as you can see in these two movies, you have some kind of large scale or large time scale events. There's some large structure shedding that happens periodically. You can see there's really long snaking structures in the wake. And so you can have kind of big shifts in the optics depending on if you're looking on from side to side. And it needs a long time to converge some of these statistics if you're trying to capture the whole thing. So we also ran the Coarse mesh simulation to kind of look at the mesh dependence. And then, so I've created quite the database out of this. So I have over about 100 terabytes of flow data to go through and look at and try and crunch this problem a little bit. So just first off, I've said that I ran this Coarse mesh and I want to see how dependent it is, the solution. And what we see from these flow quantities, I get really similar results between this Coarse mesh and the fine mesh. So at least in these flow quantities, it looks like there's some insensitivity. And then here, this is just the CP curve compared to some experiments, and we have pretty good comparison with that. There's a little bit difference in the back pressure, but for the most part, along the center line of the turret, we have pretty good match with the coefficient of pressure. So getting on to kind of the core of this problem is looking at the optics. So like I said, these index of refraction fluctuations are really weak, so we don't really have a lot of scattering of the waves that they propagate through. And you can use ray tracing to calculate the optical distortions. So at each beam angle that I look at, I have to embed a separate beam grid into my simulation. So I'll show you in a second. I have about 400 different places I want to look to survey the entire optical environment of the turret. So each one, at every time step I calculate the optics, I have to interpolate onto those grids and then integrate through, which really was kind of just a balancing act because, as you can imagine, it gets very, very concentrated near the turret. So parallelizing was kind of just weighting and balancing everything. And then doing the integration, you can just break it into chunks locally and then afterwards just nail it all through with one collective communication. So this is kind of an example of some results that we get. So using this initial beam distribution profile, this is 3 different optical wavefronts looking through the center line of the turret just backwards. And then the main thing that you see is that the further back you go, the larger the structures get. You start to see a little bit different in the convection direction here, which is due to these horn vortices. And then you can see the separation line kind of right here in the middle of the 110, but the further back you look, it's almost all large-scale structures. And then you can also see how this affects the far-field intensity pattern of the optical wavefront as you go further out. Looking at 110 degrees, looking back, it's not too bad. You can see some of these structures and how the convection of those plays a part in these little waves in the diffraction of the beam. But as you look further back, by the time you're looking through the wake of the turret, your beam is pretty much gone to nothing. It's nothing more than a flashlight. So just a quick comparison between the coarse mesh and the fine mesh, which are these solid lines here, and comparing to experiments. It looks like the trend and the magnitude is kind of good, but unlike those flow quantities, it doesn't look like we have complete convergence yet, which is a little disheartening. But it does seem like we're moving forward with something, and this is something that we've kind of seen in simulations before. The optics and density fluctuations seem to be one of the most difficult things to capture in these simulations. So moving forward, we'll have to kind of plan and see if we can do an even larger simulation to get better convergence. So this is kind of a quick overview of the Aero-optic results that we got. So this optical data was integrated and collected at almost 400 different angles surrounding the turret. And you can see the distribution of the points. This is just the hemisphere. If I just put dots everywhere the center of the aperture was. And it's colored by this value, I'm sorry, I should have shown in the last slide, of OPD RMS, which is the spatial RMS of the wavefront. And you can relate that to the far field distortion and loss of intensity. There's a relation called the large aperture approximation that you could use to look at the far field intensity just based on some kind of wavefront statistic. So this is all colored by it. And one of the first things you might see is, okay, there's 2 bumps where the largest amount of optical distortion is located. And so this is a picture of streamlines from the average flow field, the velocity of the flow field in the turret. And you can see that there's these 2 big structures that come out here and snake, and we call those horn vortices. And so this is actually a picture that was drawn by Stas Gordiev, who's a research professor at Notre Dame, and from experiments. And this is kind of what they'd gotten from the experiments, that there's all these structures, and 2 of the largest ones are these horn vortices, and they have a large impact on the optics. And we see something similar here. And so just moving forward and looking to crunch lots of data. So this is optical distortion, that OPD RMS term for 4 different aperture sizes. And then what you kind of see here, this is for versus look back angle, which is a different way of looking at it. So if you have a sphere, instead of looking kind of azimuth and then off the horizon, this is kind of looking at if it's axis symmetric, where do you look back from the front, the flow direction. So this is a little bit closer to maybe a fluid dynamics type, where you'd expect off of a sphere or this hemisphere that you'd have a similar separation point, and that's kind of what it's connected to, is that look back angle from the front of the flow. So that's what this parameter here is on the x-axis. And then what you see is pretty interesting, is that you have a lot of points that collapse onto a similar line, where you could have it only takes 1 parameter to really define what the optical distortion is. And then you have all these other points afterwards that kind of get splayed out here. And so if we take a little closer look at this, so it's kind of hard to tell with this color, but I've colored all these red, the ones that fall on this line, and then the ones that don't, I've colored them with blue diamonds. And if we show the distribution of those on this map again, it may be kind of hard to see here, but all of the blue ones fall in that horn vortex region. So it seems like in all of this red area, you can only use a look-back angle to kind of see what the optical distortion is. You could use that to parameterize it. But in the horn vortex, there's some kind of other physics that are going on that is different from this region. That's why we dump out the database, so we can look at later and try and figure out, okay, so what's going on here that's different than the rest of this region? And then we can learn a little bit more about the problem. So just looking a little further, the region that's defined by that also changes with the size of your aperture. So as you decrease your aperture, you get more points that fall on that kind of collapsed red dot curve. So that makes sense too, though, because the bigger the aperture, the more that you'll see a chunk of that horn vortex region sooner. So that jives with what the intuition would tell you, that the horn vortices have a different kind of physics or interaction with the optics that are going on. And then this is just kind of a plot of all those collapse regions. And it's kind of interesting because above a certain aperture size, which I think this is due to tip tilt removal, which is kind of a cleaning up of the optics that we use to do it. But for above a certain aperture size, all those collapsed regions seem to have a similar slope with the look-back angle. So there's something interesting to look into that too. Something that I did, which I'm kind of moving forward with hopefully in the next year, is to use some data-driven decompositions to look further at the data too. So they've kind of gotten in vogue, using POD and DMD to look at these flow fields, especially ones with a lot of complicated flow dynamics, like you could expect, where you have this kind of shedding that's periodic but has a lot of intricacies to it. So I developed a code to do this based on the tall, skinny QR decomposition methods based by Demel et al., and then kind of taken from Sayati et al. I think she's at Urbana-Champaign now too. So, so I developed this just using MPI, LePac, and BLAS. And I've gotten this code to run on over 1,000 XE nodes with a really large, dense matrix using the whole density field. So I had a matrix that was, so this is just POD, or this is the same thing as principal component analysis. It usually gets labeled. The problem is essentially you have a dense matrix, you need to compute an economy SVD on it. So I've done this with a matrix that's 200 million by 2,000. And so doing this calculation, it was a fun work in LePac and BLAS. And so there's some interesting physics that you can kind of glean from it, and connecting it to the optics will be kind of really the interesting part about it. So you can see just here, mode 1 through 4, these are kind of the oscillating. They're anti-correlated in across the center line of the turret. But these are more of a breathing mode, so you have kind of this compression and expansion that happens in the wake of the turret. So, and then this is kind of the second area that I've been doing research on in the past year using Blue Waters, is looking at the optical behavior of shear layers. So the real part is kind of looking at the spectral and looking at the structural behavior of large-scale structures in a kind of a classic fluid dynamics problem that we could still use and apply when we look at separated flows like we have in the turret. So you have a shear layer, which is essentially you have flow going one direction at the top and then going the other direction at the bottom. So what I have is two different cases that I ran and I investigated. One where the density at the top, mixing layer, shear layer, is the same at the top and the bottom, and then one where it's different. The pressure is the same on the top and the bottom, but you do it by altering the temperature. So what you get here is two different effects, where the only temperature here is going to be created by viscous and then some cooling just by the large structures accumulating in the vortex cores. So you expect to have pressure-dominated small-scale optical distortions, where in the other case, you'd expect to have temperature-dominated small-scale optical distortions, and then we can look at that and examine what do we see in the optical quantities too. So just kind of the setup, like I said, you just have flow going one way at the top and then the other at the bottom, and then the compressible Mach number, which is the difference in the flow velocities divided by the speed of sound at the mean is 0.3. So it's not, the compressibility effects really aren't huge yet. So this is kind of nice when we look at it a little bit closer with some incompressible turbulence and the statistical stuff that's been developed to study that. So the mesh dimensions, it's about 250 million control volumes. This is mostly based off of almost completely work that was done by Patano and Sakar in this Journal of Fluid Mechanics paper from 2002. The resolution for this is twice theirs based off of the initial momentum thickness, but the Reynolds number is 10 times larger. So we are still using LES because we're not doing the whole range of turbulence because he increased the Reynolds number. And then for each simulation case, I ran 3 ensemble simulations to get converged data. So just looking at some comparisons of turbulence quantities with that of the study done by Pantano and Sakar and done by Rogers and Moser, we get really good quantities comparisons with those DNS results. So the DNS results are the solid lines. These boxed ones are ones that are also presented in the 2 papers from experiments, and then black is mine. So even though the Reynolds number is 10 times larger than their simulations, we still get really good comparison with their results. And so this is kind of one of the punchlines is, so if you do the theoretical wave propagation given some kind of index refraction field, you can show that the if the density fluctuations obey some kind of log law behavior in the inertial subrange, then you'd expect the beam propagation to happen, and then you have the OPD, or the phase distortion of the optical beam, to go in that inertial range as the slope of the density plus 1. So kind of the cool thing is that we have these 2 different cases where we have the density distortion, where I show the spectrum here, and then this is the compensated spectrum. So if that is the right line, you should see a flat region. So in both cases, you see this is the density spectrum and then the inertial range. And then when you add 1, it looks like it's the exact same thing in the phase distortion, or the OPD. But really interestingly is that because you have different spectral behavior, pressure and temperature and turbulence, that depending on what's dominating your optical distortion and your density, you actually get different slopes. So it's kind of like what the simulation parameters and what's going on with your shear layer, it leaves almost like a spectral footprint on your optic distortion. And then just kind of, I think this is my last slide. You can decompose the OPD into contributions of pressure and temperature if you say that the temperature distortions are small, so you just linearize the ideal gas law. And then what you see, this is autocorrelation of the temperature and pressure OPD that I defined up here. So this is temperature for temperature OPD for these 2 cases, and this is pressure. It's pretty interesting because the autocorrelation for the pressure OPD is almost exactly the same in value and variance, and in the autocorrelation. They sit almost right on top of each other. But the temperature is drastically different. So what that kind of tells us moving forward is that the shear layer, no matter what the temperature difference is, the pressure underlying structure and distortion on the optics is almost exactly the same. So it's almost like that's always the same, and then it's really just adding this temperature distortion, and that's really what changes as you change the difference in temperature at the top and bottom. The pressure, I'm sure if you go high enough in the temperature difference, you'll start to have some effects. But at least for these moderate differences, you have almost the entire same structure in the pressure. So just wrapping it up, using blue waters to study an applied and fundamental problem for aero-optics. And through blue waters and the abilities of the I/O, and I move stuff around a lot, able to process and explore over 100 terabytes of flow and optical data. And then I also developed this DataDriven Decomposition solver, and then we can crunch several terabytes at a time. And then the link between the behavior, the optical phase distortion, flow quantities, I've been able to investigate that by looking at this fundamental shear layer problem. And then of course, I want to thank Blue Waters for all the support in the last couple of years and allowing us to run these problems. And through the past year, I've had support through this high energy laser JTOW grant through the AFSOR. So thank you very much.